There's only 20 slides. It's not that bad. So the first thing that we talked about a very long time ago, but she didn't actually have us write in our notes because I don't know what she's teaching, is the types of motions. So translational motion is the motion where particles move in one direction in a straight line. We've been talking about this for the past week. It happens in the gas state, and all the particles move in straight lines until they collide with something, and then they go in a different straight line. Rotational motion is where the molecule rotates around itself and around its own axis. This happens in liquids. The particles rotate around the liquids, but they can't just move in straight lines with translational motion because they're still attracted to each other. And then vibrational motion, which happens mainly in the solid state, is just the fact that the particle is vibrating, but it can't rotate and move past each other. So the solid state only has vibrational, liquid has rotational and vibrational, translational is in the gas state, as well as rotational and vibrational. All of those happen in the gas state. This down here, electronic motion, I don't know if this thing will go away, but it's the movement where electrons move freely through the orbital. So in metallics, where they have that C cloud, so the higher the temperature, the faster the electrons move, and the more it can conduct electricity. The next thing here, this is the only concept really from this that you need to know, that gases are super far apart and move like this, and then solids and liquids are close together. Gas laws. So this is the combined gas law. Usually they don't have it with the N, but she had it with the N, so I threw it in there. And from this, you can get all your other laws. So you don't need to memorize Boyle's, Charles, Avogadro's, or Gay-Lussac's because they're all in here. Boyle's being if you hold moles and temperature constant, PV equals PV. So if you make more volume, the pressure is going to go down because there's going to be less area. There's going to be less walls for them to hit and more area for the particles to move around in. Whereas if you decrease the volume, there's going to be less space for them to move around in and more walls for them to hit, increasing the pressure. In Charles's law, pressure and the moles are held constant, and you have volume and temperature. So V over T equals V over T. This is assuming that you can freely change the volume of this container. So if the temperature gets very high, therefore the pressure is going to be high. But if you can freely move the container, then the temperature is going to get so high and the particles are going to move so fast that they're going to make the container expand instead of expanding the pressure. And so that's why Charles's law exists if pressure is held constant. Gay-Lussac's law is when we just have pressure and temperature. So when you increase the temperature, there's going to be more pressure because the particles are moving around. The volume this time is held constant, so it can expand, so the pressure is going to go up instead of the volume increasing like it did back here. And Avogadro's law is volume and number of moles. I did that wrong here. I feel bad now. So yeah, the volume and number of moles. Basically, if you increase the number of moles, then it's going to make it so that there needs to be more room for the volume to increase as the pressure is being held constant. And these are some other sections. So PT over P over T is P over T, V over N is V over N, and NT is NT. Those don't have names, but they are there if you need them. So the next thing is ideal gas law. PV equals nRT, as we've seen.
PV nerd!
Thank you, Lauren. So STP is an important thing to talk about right now. We're saying that we have 1 mole at 1 atmosphere at 273 Kelvin with a volume of 22.4 liters. If you plug that in, you'll get an R value of 8.206 times 10 to the negative second atmospheric liters over moles Kelvin. So at STP, if there's 1 atmosphere, 273 Kelvin, and 22.4 liters, you're going to have a mole. This gas constant that can then be used in PV-nRT to solve for something if you don't know one of these, even if it's not at STP. Now, with that, you can get a lot of different problems, but just write down what you know. And once you write down what you know, you might be able to see, I have PVTN, or I have pressure, volume, and temperature. So I'm solving for moles, I can find moles. Instead of just looking at the problem with a bunch of numbers and being confused and lost. Write down what you have and what they are attached to. So now let's do one of our density equations. You only really need to know what's here in yellow, which is gone now. But PV equals nRT. N is the number of moles, so that's mass over the molar mass. Grams per mole. So grams per mole is the molar mass. So instead of saying N, we can say mass over molar mass. PV equals mass over molar mass times R times T. Now, if you rearrange that, you have your equation for molar mass. You just divide the PV over, and you have molar mass as M over PV times RT. Now, mass over volume, as you can see right here, that's density. So we can say that the molar mass is density over pressure times RT. So you don't really need to know how to do that. If you just memorize molar mass is density over pressure times RT, you might get one problem like that on the quiz. Partial pressures are more simple than they seem. If you're told you have 0.5 atmospheres of A, 0.75 atmospheres of B, and 1 atmosphere of C, the partial pressure of B is 0.75 atmospheres. It's just the amount of pressure that gas exerts. So when they're all combined, add them up and you get the total pressure. If you add all of them up and you get 1, unless the total pressure is 1 atmosphere, you found the mole fraction, you didn't find the partial pressure. So the mole fraction is the number of moles of the part, so the number of moles of hydrogen in a combination of hydrogen, oxygen, and xenon gas over the total number of moles will give you your mole fraction. Now, since moles are directly related to pressure, the partial pressure, or how much pressure one gas exerts over the total pressure, gives you the same thing. So to find the partial pressure, don't divide how much you have of what pressure you have of this by the total. You're finding the mole fraction. It's just how much pressure you have of the one particular gas. Now, collecting gas over water. It seems super complicated here. All we're saying is that we're taking zinc hydrochloride and we are evaporating it to produce hydrogen gas. That's what you'll get out of this. And you do that over water, and so you're going to have hydrogen gas, and you're also going to have water vapor in here. So they'll give you the total pressure, and they'll tell you what temperature it is. So you can find it. They'll tell you what the pressure of water vapor is at that temperature, and you'll know the total pressure. So using your partial pressure equation, you can find how much pressure your hydrogen gas alone is exerting, and then just plug that into PV and RT, because they'll give you all the other values you need, and you can find whatever you're trying to find, whether that's moles or volume. Reactions with gases. She didn't go over this. I can't really find a way to teach it other than just give the 4 problems they gave us. So they're pretty simple if you just understand what we're talking about. So when you get an equation like this, we're saying 2 moles of water is going to give you 2 moles of hydrogen gas and 1 mole of oxygen gas. Same way of saying 2 particles of water is going to give you 2 particles of hydrogen gas and 1 particle of oxygen gas. So if we're saying we have 1.2 liters of oxygen at a temperature of 315 K and a pressure of 0.912 atmospheres, and we're trying to find mass of H2O, we're going to need 2.4 liters of hydrogen, since if there's 2 moles, 2 particles, 2 liters of water, there's 1 mole, 1 particle, 1 liter of oxygen gas. So if there's 1.2 liters, you'll need 2.4 liters of of water, and then just plug the other values into PV and RT. So now it can get a little more complicated. You might not be able to just multiply this number by 2. So if we're trying to find volume of oxygen gas, we have 52.7 grams of aluminum. Always convert that into moles. And then we have, if there's 4 moles of aluminum, there's 3 moles of oxygen. So take your moles of aluminum over 1 and create your proportion with 4 over 3. So if you have, say this ends up being 12 moles of aluminum, you'll multiply that by 4, divide by 3, and then you'll get the amount of moles of now oxygen, not aluminum, that you need, and then you can plug the rest in to PV-nRT. So it's the same thing here. What mass of lithium is required to react with 56.6 milliliters of nitrogen? Well, you have 56.6 milliliters of nitrogen, convert that to liters, and then say if you have 1 liter of nitrogen, you have 6 liters of lithium. So take your 56.6, create a proportion with the lithium and nitrogen that you have from the equation, and solve. Okay, so for the final problem on here, we're given our formula, and we're saying we're given the volume, we're given the temperature, and we're given the pressures of both of the reactants. We need to first find the limiting reactant. So what we're going to do for that is we're going to take our values that we have here and just plug them into PV-nRT. And we're going to find the amount of moles of both of them. So for CO, this is the pressure, and then convert it to atmospheres. And then the volume, gas constant, temperature, to find here the number of moles, and we found the two number of moles. That doesn't mean CO is your limiting reactant. This is because if you come down here, you can see that from the equation, 1 mole of CO is 1 mole of CH3OH, but 2 moles of H2 only produces 1 mole of this. So we have to take our moles and then use our conversion. So 0.23, and there's 1 mole of this and 1 mole of this, so the number's going to stay the same. But here we have 0.034 moles. Now, we're saying that there's 2 moles of CO3OH in 1 mole of H2. So we're only going to have 0.017 moles of CO3OH. That means that CO3OH is your limiting reactant, and all you have to do now is take CO3OH and the amount of moles and convert that to grams using the molar mass. So the same conversion and how you're setting this up is the way you did all the previous problems when I say conversion factor. That's how you're doing it. You're setting up 4 moles of aluminum and 3 moles of O2, or 2 moles of water and 2 moles of hydrogen gas. That's how you're setting those up. That's really all you need to know from this. Next is kinetic molecular theory. There were 5 things here. There's not really much to this, although she spent a lot of time on it. 1, gases are in random motion. There's no force of hand moving them a certain way. We're ignoring the volume of the gas. This is why PV-nRT works. We're saying the gas does not take up any volume in the container. Obviously, this isn't true, and we'll get to that in a second. There are no intermolecular forces between the gases at all. And there are elastic collisions, so we're not losing any energy when they collide. Temperature and kinetic energy are directly related. So the same temperature of 2 gases makes the same average kinetic energy. That doesn't mean the same total. Total kinetic energy is basically pressure. But the average kinetic energy is directly related to the temperature and only the temperature. It doesn't matter what gas you have. It's always going to be the same average kinetic energy if you have the same temperature. Now, here we have the diagram that we talked about with that. The area under each of these curves is the same. But we're saying if it's a very cold gas, the particles aren't going to be moving very fast, and they're going to be super highly concentrated. But if you have a hot gas, they're going to be moving faster, but there's going to be a bigger distribution of how fast or slow the particles are moving. They're not all moving at the same rate, but the average rate is the temperature we say it is. So we use one equation for that, Ke equals 1/2 mv squared. And with that, we're saying if you have a super big particle, it's going to have low velocity. If you have a super small particle, it's going to have high velocity, but they're going to have the same average kinetic energy. Now, she didn't show us the derivation for this, but just remember that Ke is 3/2 RT, and you're using 8.314 joules per mole Kelvin. That's on your sheet, on your equation sheet. If you're given a problem where you have the temperature and you're trying to find kinetic energy. Now, because temperature is directly related to kinetic energy, if you double the temperature, you're doubling the kinetic energy. Now, everything that we just talked about isn't true because gases aren't ideal. Gases can condense, and when they condense, the particles are closer together and they experience intermolecular forces. And they do take up a volume, whether that be small. So they're not ideal if you have a low temperature. As you can see here, if they're moving very slowly, they're going to get attracted to each other better. Whereas if they're moving fast, you might not have to worry about that. High pressure. If you have a high pressure and also low volume, the particles are going to be forced to be closer to each other and they're going to be hitting each other more often, so those intermolecular forces are going to come in. If you have high IMFs, like if you have hydrogen bonding, those particles are going to be attracted to each other. Or if you have really big molecules, those particles are going to be attracted to each other. This is why we always say it's an ideal gas when we use PV equals nRT and assume that these things aren't affecting it. You just have to know that these 5 things are affecting a gas, and this is what a real gas does. But for our sake of doing calculations, we're going to pretend like there's no force between them and they're completely independent. This is the last slide. These are all the equations you need to know. So PV over NT is PV over NT, that's combined gas law. PV equals nRT, that's ideal gas law. KE equals 1/2 mv squared, that's your kinetic energy, average kinetic energy, well, yeah. And then K equals 3/2 RT is also a kinetic energy equation, depending on what you're given in the problem. Molar mass is density over pressure times RT. We do need to know that one because you might get a question like that. And then your partial pressure and your mole fraction. And that's it.